Welcome to Seiche and Slosh, and I'm Tom Irvine. Hope you enjoy this unit today. So here's a Seiche in Lake Geneva, Switzerland, and one wavelength of the standing wave then equals twice the length of the lake. So a Seiche is a standing wave oscillation in an enclosed or partially enclosed body of water. It could be a lake, reservoir, harbor, even a swimming pool. It can be triggered by earthquakes, atmospheric pressure changes, or even strong winds. And in earthquakes, the oscillation occurs because the ground shaking tilts or accelerates the water basin, and then the horizontal ground motion causes the water mass to slosh back and forth. And if the forcing frequency is close to the natural sloshing period of the basin, then a resonant amplification can occur. And after the earthquake stops, then the water may continue to oscillate for minutes and even up to several hours. And seiches, in fact, were observed in swimming pools across the United States during the famous 1964 Alaskan earthquake, which we've discussed in a previous unit. And here then is going to be Lake Geneva, and the town of Geneva, or the city of Geneva itself, is in the lower left portion of that crescent. So the Seiche fundamental frequency is 1 over 2L, L being the basin length, square root underneath gravitational acceleration, then H will be the water depth. And then the period is going to be the inverse of that Seiche fundamental frequency. And for Lake Geneva, its period is going to be about 73 minutes. And the amplitudes in Lake Geneva, under normal conditions, maybe 5 to 20 centimeters, and occasionally up to 50 centimeters or more. It's an interesting photograph there. And here is the Great Lakes in the United States. And these are going to have longer periods than Lake Geneva because they're larger bodies of water. And Lake Superior at the top is 7 to 8 hours period for its Seiche. Lake Michigan is about 4 to 5 hours. Lake Huron is about 3 to 4 hours. Erie, 2 to 3. And Ontario, also 2 to 3. Now, seiches in the Great Lakes they're always there, present at some low amplitude level. And the lakes are so large that they're constantly being nudged into oscillation by the passing weather. That can be pressure gradients, wind stress, etc., but not really much by earthquakes. That's not a very active seismic area. So mostly weather rather than earthquakes. Here is a Rayleigh wave. We've talked about Rayleigh waves before. They're surface waves, and they have a rolling motion, but the motion of the particles, or water molecules, or the ground, whatever it might be, is counterclockwise. We call that retrograde. So when a Rayleigh surface wave passes, then the ground motion includes both vertical and horizontal displacement. The ground motion produces a temporary tilt of the basin floor. Then the resulting pressure gradient triggers a standing pressure wave. And this is essentially an initial condition excitation rather than a resonance. So earthquakes can trigger seiches, but the excitation occurs mostly as an impulse rather than sustained resonance, because typically the frequency mismatch is extremely large. The impulse comes from the arrival of long period surface waves, especially those Rayleigh waves. And earthquake shaking, by contrast, is usually a broadband transient input rather than a steady sinusoid, which would be more efficient at exciting resonance. The basin can then respond strongly to the impulse component, and long natural periods mean the water may continue oscillating long after the shaking ends. And direct resonance with the dominant structural frequency content of the earthquake is usually unlikely for very large lakes, but I suppose can happen for smaller ones. Okay, damage mode. So this is actually part of a tank, and we have then the base plate of the tank, and there's water molecules, or it could be some other fluid. And here's plastic hinge, which we talk a lot about plastic hinges for beam and column connections for building structures. But in this case, it's a tank rather than a building. And there's a weld here, and at this corner, there's something called an uplifting displacement, or edge, rather. And we're going to be talking about uplifting displacements a bit. Now, sometimes these tanks are bolted into the ground or anchored into the ground, and sometimes they're not, and we'll talk about that later on. So during earthquakes, liquid stored in tanks oscillates, and this is, as we mentioned, sloshing, or also known as convection, and damage can result. So the roof can be damaged from liquid impacting on floating or fixed roofs, spills over tank walls leading to environmental release or fire in the case of a petroleum product, increased base shear and overturning moment. We'll talk about those effects as we go along. And then we are showing this tank uplift on the right, or if there are anchors, then they could potentially fail. And tanks can also undergo buckling modes. There are several types of buckling that are unique or somewhat unique to tanks. So here's a tank from the 1999 Turkey earthquake, and the buckling of the top part of the liquid storage tank was caused by liquid sloshing during that earthquake. So you can see it's all bent out of shape there. This is an elastic plastic shell instability caused by compressive hoop straps generated by the hydrodynamic sloshing pressure. We're going to be talking about that in a future slide. I'll even give an equation for that. So during earthquakes, liquid stored in tanks oscillates, and that's sloshing or a convecting response. And this can cause then the roof damage from the liquid impacting on the floating or fixed roofs, spills over tank walls leading to environmental release or fire, and increased base shear and overturning moment, and tank uplift and anchor failure in the unanchored tanks. And this is going to be our two-mass spring model. It's a simplified model, but it's a very common model for modeling slosh and other effects in tanks. And we're going to take this liquid, and then we're going to divide it into two masses. There's the impulsive mass and the convecting mass. We'll talk about those, and then we're going to have several heights. We have the height to the top of the tank. We've got HW is the nominal water or liquid height, whatever that fluid might be. We've got then H sub C will be then from the ground to the center of the convecting mass, and then H sub I will be from the ground to the center of the impulsive mass. And M sub C is the convective mass, N sub I then is the impulsive mass, and we have two springs on either side. We've got a Kc over 2 and a Kc over 2 and a Ki for the impulsive divided by 2, and likewise on the other side. So instead of complex fluid simulations, engineers represent the liquid as a system of discrete masses to calculate the forces and the torques exerted on the tank. Now this model goes by several other names. So it's the Slosh-Hausner two-mass model, also referred to as a two-pendulum or multi-mass spring model. It's a simplified mechanical analogy used to predict the dynamic behavior of liquid moving in a container, such as a tank. And of course, it separates the liquid response into the impulsive and convecting or sloshing components with a conceptual, not physical, dividing line. The convective layer undergoes sloshing, so that's the top layer. It's going to have the slosh. You can see the slosh waveform at the surface, while the impulsive layer remains rigidly attached to the tank. So we're going to take a look at the convecting on the left and the impulsive on the right. So the convecting or sloshing mass is at the top region of the liquid. Water or liquid near the free surface, it moves like a wave, producing those slosh oscillations with a long period motion, causing liquid surface displacement at low frequencies, and yes, large displacement. Generating a slosh wave height may cause overflow if freeboard is insufficient. And then the typical period is going to be from about 3 to 10 seconds, depending on tank diameter and water height. Let's go back and define freeboard, because that's an important concept. So if we take H minus HW, that is the freeboard. It's the extra space available for the sloshing displacement. Now the bottom mass is the impulsive component, and then the liquid moves together with the tank wall, resembling a rigid body acceleration with high frequency response in a short period, small displacement. Puts a large force on the tank wall, and typically with a period of 0.1 to 0.5 seconds. Here's our model again, so we got a couple of repeat images to help us keep everything straight. So again, MC is the top mass, the convecting part. Represents slosh. It's got a HC, a height. It's got the springs, KC divided by 2 and KC divided by 2. And these springs simulate the sloshing restoring force due to gravity. Then the impulsive mass, n sub I, represents the liquid that moves with the tank wall. Yes, I know there's some repetition here. It has a height h sub I and springs k sub I over 2 on either side. And these springs represent the tank wall stiffness, plus also the hydrodynamic coupling. And here's that familiar image again we saw before. So the convective component mainly drives the free surface displacement, roof impact, overflow, and then the freeboard requirements. Again, freeboard is the extra room available at the top. The impulsive component mainly drives the base shear, the overturning moment, the shell compression, and the anchor forces. Now here's a community water tank, fairly large one, up in the hills. Kind of looks like California. To show that you probably have one of these maybe in the area where you live, or you've seen these sorts of tanks before. Height and forces. So we're going to do some calculations for forces and then the overturning moments. So we've got D will be the tank diameter, H the total liquid height, including the vertical displacement, then due to sloshing, HW the nominal height of the water or liquid. If I say water, you can substitute liquid. Height of impulsive mass, H sub I, H sub C, the height of the convecting mass. So the impulsive force for the lower mass, the impulsive mass, M sub I. So F sub I equals M sub I, and SA is a function of T sub I, which we need to define, and we'll do so shortly. And that acts at height HI and governs shell stresses. And then the convecting force from the top mass, FC equals MC, and then there's that S sub A again, but now it's a function of T sub C. So then T sub I is the period then for the oscillations of the impulsive mass, and T sub C is the period for the oscillations of the convecting mass. Now this SA is a function of T, whether it be T sub I or T sub C, is the peak acceleration response of a single degree of freedom oscillator with a natural period, T, subjected to the earthquake motion as taken from ASCE 7-22 response vector or elsewhere. And the convecting sloshing forces are usually smaller than the impulsive forces, even though the slosh displacements are large. So F sub I we expect to be greater than F sub C. So the total base shear is then V, and it's F sub I plus F sub C. And that can be used for anchorage and shell shear and so forth, sizing fasteners, and the anchor bolts. And then the overturning moment is going to be M sub 0, and it's F sub I, H sub I from the impulsive, and plus F sub C, H sub C from the convective. And the overturning moment is used for uplift. We talked about uplift before, anchorage design, shell compressive stress check, and foundation stability. Slosh wave height delta, delta sub S. So the maximum vertical displacement of the sloshing liquid at the shell is defined by delta S as follows: 0.2 times R being the nominal tank radius, and then we've got A sub F, which is going to be a spectral acceleration coefficient for the sloshing or convecting mode. So we need to figure out where A sub F comes from. So this height determines the necessary freeboard, the distance between the liquid level and the roof to prevent the wave from striking the roof structure. Okay, spectral coefficient. So we're going to refer to a API 650 standard to get our A sub F, and that depends on where the convecting period Tc falls relative to the transitional long period T sub L, and T sub L represents the boundary where the seismic ground motion transitions from being constant velocity to constant displacement, and comes from ASCE 7-22 based on the geographical location. Then S sub D1 is the design spectral acceleration for a 1 second period from ASCE 7-22. So we need both API 650 and ASCE 7-22 to make this calculation all come together. So if Tc is less than or equal to TL, again Tc is the convecting period, then AF is equal to 2.5 K. Well, we need to define what K is, and we'll do so shortly. SD1, well, SD1 is going to come from ASCE 7-22 and then 1 over Tc. And then we have, if Tc then is going to be greater than TL, then we have AF is equal to 2.5 K SD1, and now we've got TL divided by Tc squared. So the K factor can be cross-referenced to a seismic use group, and it's going to be 1 for standard storage tanks. They're not high risk. It's going to be equal to 1.25 for tanks storing hazardous materials that could impact the public if leaked. And that will be equal to 1.5 for essential tanks, fire, water for a hospital, emergency fuel, etc. So if you want to be conservative, then set that K value equal to 1.5. And here's some sample Slosh spectral coefficients and typical A sub F values. So for a low seismic region, then A sub F could be up to 0.05, or for moderate seismic region, 0.05 to 0.15, high seismic, 0.15 to 0.35, and for a very high seismic region or with a soft soil, then occasionally that coefficient A sub F can be above 0.4. We'll have to do some MATLAB exercises. So here's the main GUI package and structural dynamics, and then to seismic, and then we'll go to select analysis, API 650, and Slosh and analyze. And we're on English units. We'll be on Slosh wave height. So the height determines the necessary freeboard, which is the distance between the liquid level and the roof to prevent the wave from striking the roof. Diameter of our tank is 150 feet, fairly large. And then our coefficient is going to be A sub F, and it's going to be 0.1. And here's a little reminder chart that we just saw on the previous slide, just as a guideline. So we're assuming that we're right in the middle of a moderate seismic region, and then we'll calculate. And then for our tank diameter of 150 feet, then the slosh wave height is 18 inches. So that's important to know. Next, we're going to go and take a look at the lateral force tab, same API 650 tank slosh strip. We have to add some parameters here, so we'll have the top convective mass, that is 60,000 lbm, bounce mass. The bottom impulsive mass is going to be 340,000 LBM. The top convective height is 36 feet. And then the bottom impulsive height is 11 feet. And again, those are referenced to the ground level. Let's go to input SA method. So SA is a function of the period t, is the peak acceleration response of a single degree of freedom oscillator with a natural period t, subjected to the earthquake ground motion, is taken from ASCE 722 or elsewhere. So our value today will be 0.2 Gs. We'll calculate. And here are the results. So we have the parameters, and the impulsive force, then it's going to be 68,000 pounds force. The convective force is going to be 12,000 pounds force. And then if we add those two forces together, then the base shear is going to be 80,000 pounds force. And our overturning moment is going to be 1.18 million foot-pounds. And then the spectral acceleration, which is actually an entry parameter, SA, is 0.2 G. So the results. So the base shear is useful for a sliding check and an anchor and shell to bottom design. And then the overturning moment is useful for anchor bolt tension, uplift and soil bearing pressure, and typically is the governing parameter rather than shear. The impulsive force, Fi, then we can take that and do some calculations for shell stress using API 650 Appendix E. We can calculate the hoop stress from hydrodynamic pressure, the anchor demand, and then the convective force and the sloshing effects and the freeboard and the roof impact. So that is the usefulness of the results. And for the hoop stress, then we are going to sigma sub theta z is equal to the total pressure at height z. So that would include hydrostatic plus any dynamic forces. And then we have r is the tank radius divided by the shell thickness t. So the total pressure then is the sum of the hydrostatic and impulsive pressures, and I just mentioned that. The convective force is typically excluded from shell stress since it acts on a free surface. The maximum stress tends to occur near the bottom of the tank. For a hydrostatically loaded upright cylindrical tank with a typical open top, the shell carries hoop stress, but essentially no longitudinal membrane stress. And here is a tank oscillation. There's a standing wave that's formed. So you can see the nominal free surface and then this half wave for the oscillation. So we've got an equation for an upright circular cylindrical tank for the slosh frequency, and that would be for the convective slosh. And the fundamental slosh frequency, then F sub c, 1 over 2 pi square root. And underneath 1.841 G divided by tank radius r. Here's our hyperbolic tangent, and then the argument is 1.841 times h, the liquid depth. And then, of course, r is the radius. And then the convective period, Tc, is equal to 1 over the frequency Fc. So for a partially filled spherical tank, we have a different equation. It's Fn is 1 over 2 pi, and then square root underneath the g, and r effective, the effective radius, which is the curvature at the free surface. And for practical purposes, we can just do a quick approximation and say that the effective radius is the same as the actual radius. Do a little MATLAB exercise here. So go back to structural dynamics, to seismic, to API 650 tank slosh, where we just were a few minutes ago. This time we're going to go to the tab for slosh frequency. We'll still be in English units. Here's our 150-foot tank. We have a height of 40 feet. And then the convective slosh results are going to be the frequency of 0.123 hertz, and the equivalent period is about 8.14 seconds. And that's within the range or family of a typical period. Of course, depends on diameter and height. Okay, tank anchoring. So we have two approaches. We can have the tank bolted down, or it can be a self-anchored tank that doesn't have any anchors. So as a practical observation, most large crude oil tanks are self-anchored because the liquid mass is enormous. The weight alone usually prevents overturning, and the anchors would be extremely large and expensive. So for the anchored tank, then the anchors will prevent or at least limit uplift, but with the self-anchored tank, then that uplift may occur around the outer circumference. Anchored tank, minimum rocking. Self-anchored tank could have significant rocking. Seismic resistance, while the anchored tank, we have bolt tension plus the weight, and self-anchored weight only. And then our failure concern for the anchored tank is the bolts going into an excessive tension, whereas self-anchored tank, we can have shell buckling. Typical use, anchor tanks, smaller tall tanks in high seismic areas, and then self-anchored large oil tanks with heavy contents. Remember that image we saw earlier today with the 1999 Turkish earthquake, and there was that buckling at the top of the tank, and that was most likely then a large crude oil tank that was self-anchored. So API 650 Appendix E explicitly checks uplift for unanchored tanks and determine whether anchors are required. And then the two seismic limits that are evaluated are shell compression. We're going to see an image of something called elephant foot buckling here shortly, and then bottom plate uplift. And if the uplift exceeds allowable limits, then anchors must be added. Let's talk more about some tank uplift. The image on the left is similar but slightly different from one we saw earlier today. We have the base plate, there is an uplift length, there's a connection rotation angle, and a plastic hinge formation in the base plate, and then the shell walls. And then on the right is a top-looking down view that shows we have a multi-axis stress state with hoop stresses and then a radial stress as well. Buckling notes. So on the left we have diamond buckling, and on the right we have elephant foot buckling. So the sloshing wave creates localized pressure at the top of the shell, and if the shell is too thin, the slap of the wave can cause elephant foot buckling at the bottom, or diamond buckling at the top, or diamond buckling could be elsewhere in the tank. Tank roofs. On the left, fixed roof. On the right, floating roof, both containing liquids with vapor as well. So floating roofs then eliminate the free liquid surface, effectively suppressing convective sloshing loads that are primary cause of earthquake-related tank damage, such as roof seal fires and liquid overflow. Our floating roofs increase the impulsive hydrodynamic loads on the tank shell and foundation, since more of the liquid mass moves rigidly with the tank shell rather than sloshing independently. The roof structure itself becomes then a seismic vulnerability. Support legs, seals, rings, and rolling ladders are all susceptible to earthquake damage, and a sudden floating roof can trigger a catastrophic full surface fire. Overall floating roofs, the one on the right, represent a trade-off rather than a net seismic improvement, and design standards such as API 650 Appendix C require special seismic detailing to manage their unique failure modes in active seismic regions. Some damping notes. So the image on the right is actually from a NASA document, and certain launch vehicles anyways, have liquid propulsion tanks. Others have solid propellant. And if there's a liquid propulsion tank, then sloshing is a risk. And it's very common to have baffles, such as the annular ring baffle shown on the right. So sloshing effects are calculated using a lower damping value, usually about 0.5%, compared to structural impulsive mass, 5%, because liquid friction is much lower than structural damping. Liquids like liquefied natural gas, LNG, and water have very low kinematic viscosity, leading to minimal internal friction during oscillation. The 0.5% damping value then for the slosh is a realistic or even slightly conservatively low estimate for the convective sloshing component for low viscosity liquids. High viscosity liquids like crude oil then tend to have higher kinematic viscosity, which increases energy dissipation as the liquid layers slide against each other and the tank walls. For these heavy contents, the actual damping may be slightly above 0.5%, though design codes such as API 650 often maintain the lower value to ensure a conservative safety margin for wave height and freeboard requirements. And internal baffles act as energy sinks by forcing the liquid through small openings or round obstructions, artificially increasing the damping ratio far beyond the natural 0.5%. Now in community water tanks, then baffles are typically not going to be used because they can lead to some potential contamination problems, for example. So I'm not really sure how much baffles are used in storage tanks outside of aerospace, but this is available. Of course, baffles are definitely used in the trailers used to transport, say, gasoline to your local gas station. Okay, water towers. Water towers are not just tanks. Well, what this is a cantilever beam, a very tall cantilever beam with an end mass. That's what it's acting like. And there can be some significant dynamic amplification. And the governing behavior then is the structural effects and then the fluid coupling that occurs due to the fluid in that spherical tank there mounted at the top. Here is a water tower natural frequency. I don't have this in MATLAB, but I need to take an action item to put this in. So let's assume the shaft, then that's the cylindrical support, is a linear elastic with a uniform cross-section. The tank is rigid, no shelf flexibility. The soil is rigid, fixed base. For soft soils, soil structure interaction reduces F sub n further. And small amplitude, linear type vibrations. So here is our fundamental natural frequency equation. 1 over 2 pi square root. In the numerator, 3 elastic modulus, area moment of inertia, divided by the length cubed. And in the denominator, the mass of the tank. And then its water contents, 0.67 times the water mass, plus 33 divided by 140 times the mass of that support shaft. And there's a note that the 33 divided by 140 factor is the classical Rayleigh correction for a distributed mass cantilever contributing to tip oscillation. Okay, Seiche and Slosh mitigation. We'll talk about this. So we talked about LNG, that liquid natural gas or liquefied natural gas, and petroleum tanks and large water reservoirs. So increase freeboard to prevent overtopping. And of course, freeboard is the vertical distance between the normal liquid surface and the top edge of the container. Install internal baffles to dissipate wave energy. Again, not altogether sure how common that is, but that certainly is an option, but maybe not for the community water tanks. Strengthen walls and tank shells for sloshing loads. Provide anchorage and strong foundation. Perform dynamic sloshing analysis during seismic design. Account for both impulsive and convective sloshing mass components. Guard against elastic plastic shell buckling, such as that elephant foot that we saw from compressive hoop stress. And there's several design codes to take a look at. We've mentioned API 650 several times. There's also a Eurocode 8 and a couple other standards there at the bottom. So Seiche and Slosh mitigation for harbors. So harbors, marinas, semi-enclosed basins. The Seiche, they're excited by wind, atmospheric pressure jumps, tsunamis. We'll talk on the next slide about a medial tsunami. Of course, an earthquake can be a source of a tsunami as well. Resonance occurs when the forcing period matches the basin's natural Seiche period. Modify basin geometry to avoid resonance. Design harbors with wave damping geometry. Use breakwaters and absorbing boundaries to reduce reflected wave energy. Maintain adequate berth clearance and mooring design for surge motions. Provide freeboard on quay walls and bulkheads to prevent overtopping. Perform basin response analysis to identify amplification, harbor resonances, and something called a harbor paradox that I need to take an action item to look that one up. And then monitor with water level gauges to capture Seiche and medial tsunami events. Got one more slide. It's just sort of an appendix. It's what is a medial tsunami? So we think about a tsunami being generated by an earthquake, but those are the classic ones that can cause a great deal of damage. But medial tsunamis are a wave driven by atmospheric forcing, not seabed motion. So meteorological tsunami, triggered by moving pressure, wind disturbances, squall line, fast cold front, derecho, pressure jump, amplified by a Proudman resonance. The disturbance travels near the long wave speed, pumping square root g times h of the product, pumping energy into the wave over a long fetch, most efficient over broad, shallow continental shelves, further amplified at the coast when a bay or harbor Seiche period matches the incoming wave period, harbor resonance. Explains why certain harbors are more prone to be struck repeatedly while others stay calm. And as a typical signature, water level swings of tens of centimeters up to 2 meters, strong harbor currents, periods of minutes to tens of minutes, often arrives on an otherwise calm day after the storm has passed or while it's far offshore. Been documented in the Mediterranean, the Great Lakes of the United States, and U.S. East Coast and Gulf Coast. So I hope you enjoyed the unit today. Thanks for coming. More fun next time we meet. Bye for now.